Let's just get started. So, the first question, what is the next number in the sequence 4, 5, 9, 14, 23? So, if you look at the difference between these numbers here, so there's a difference of 1 here, difference of 4 here, difference of 5 here, and a difference of 9 here. So then we all know that 1 plus 4 is 5. Wait, sorry, it's like 1 plus 4 is 5. Then 4 plus 5 is 9. And then, so 5 plus 9 equals 14. So then we know that 23 plus 14 equals 37. So it's a little bit of Fibonacci with like the difference between these numbers here. So the answer is 37. All right. So which of the curves shown in the figure is not a trajectory in the gravitational field of a central star at the point x equals 0, y equals 0, marked by the star symbol? Okay, so we know that trajectories, they can be ellipses, they can be hyperbolas, they can be, I guess parabolas as well, they can be circles, okay? So if we look at this one, number 5, so this one here, that's fine because it's a kind of space objects, coming through, coming out. So that's a hyperbola, that's okay. Number 1 over here, this one's okay because it's an ellipse. That's like a comet or, I guess, a very, very weird kind of planet. And then we have 2 here, the smaller circle. This one's okay because it's equal distance in the middle. So number 2 is okay. Number 4 here, this is a parabola. So that's okay as well. But if we look at number 3 here, it's a circle, yeah, but it's not at the centre. You can see the radius is a different length, say here and here. And that's not possible because if you have a star, it's either going around in like a perfect circle, that's meant to be a perfect circle where these both lengths are, or it's going to be going around in an ellipse, but it's not going to be going around in a circle like, how can I draw like a bad circle? Like that, yeah. No, it's not going to be going on like that. So the answer is E. 3 is not a trajectory. All right, so now question 3. Which combination of units is the odd one out? So we need to know a bunch of formulas for this to work. Or I guess you could just like try and find it from a bunch of old formulas, but it's better to use it from other formulas. So with this, I'm not going to look at A first, that's quite complicated. But if you look at B, you can say that this is A as in an amp, T as in like B, and L as in a meter as in L. So basically this is F equals BIL. So you go Tesla amp meters. So this one's a force, we know that. This one here, C, kilogram meters per second squared. We should already be able to recognise that as F equals ma, as this is acceleration and this is mass. So these two are forces. So which combination is the odd ones out is going to be one which isn't a force, okay? So if we look at D, this is joules per meter. Well, if you remember, force equals work. Wait, sorry, not work over distance. If we say that, oh yeah, sorry. If force equals work over distance, then that is that one. So here we go, F. And if we go here to E, we have Coulomb meters per second, which is Q times V. And I'm not sure if that's a force, so we're going to come back to that one. If we look at A here, this is Coulomb's volts per meter. Well, a Coulomb here, we have Q, volt with that, over D, okay? Now, if you remember the equation E equals V over D, yeah? So we can place this with F equals QE, because, or as you may know, is in your formula book, EQ, because F equals EQ. So then this one is also a force. So the odd one out is E. Okay, that one was quite hard, but anyway. 90 people enter a maze. At each junction, a third will go left and 2/3 will go right. after 3 such junctions, what is the most likely combination of turns of people? Right, well, we can just draw a kind of a diagram. So if we just do it like this, we go left, 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 right, 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 and then here we go left, right, we go left, right, left, right, left, right. Okay, so these are 3 junctions, okay? So left, left, and I guess I could say this one, or I'm going to put it at the end actually, just to make it easier. Okay, so then we have right, left, right. Going to redraw this one here. Oh God, sorry, what am I doing? Okay, left, right, left, right, left, right, right, right. Okay, I think that's all of them. So a third will go left and 2/3 will go right. So we know the probability of going left equals a third, and the probability of going right equals 2/3. So at first glance, perhaps like going right, right, right would be the highest probability because it's 2/3 cubed. But there are different combinations because although, for example, left, right, left has less of a probability, there are 3 of those because we have left, right, left in the ones I just drew, and then we have right, left. Wait, we have left, right, right. Wait, so I'm just gonna draw it out of this. Left, right, right. This equals a third times 2/3 cubed. So where would we have 2 rights and a left? Well, if we have 1 here, and then 2 rights. No, sorry, we have left, right, right there. We have right, left, left here. And we have that's all of them, I think. Right, and right, right, left. No, so we have 3 of these. So 3 times that. And similarly for left, left, right, we have 3 of these. But it's 3 times 2/3 times 1/3 cubed. And then we have left, 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 but we just have 1 of these, which is 1/3 cubed. And then we have right, 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 which is 2/3 cubed. So this is times a third. Wait, no, no, it's not. Okay, so we can clearly see that it's between this and this because we have a 3 times that. So these are like fractions, and you can see that quite clearly. So if we go left, right, right, this equals 3 times 2/3 squared times a third. So this equals 3 times 4 over, this is 3 cubed here. So this is quite clearly 4 over 9. So if we go left, left, right now, this is 3 times 2/3 times 1/3 squared. So this is 3 times 2 over 3 cubed, which is 2 over 9. So clearly that left, right, right is the most likely combination, as it's more likely than right, 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 left, 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 right. Yeah. Alright, so next question 5. A person drinks many cups of tea. The first cup the person drinks is filled completely. They don't want to drink too much tea in total, so the second cup is filled with only a fraction of the tea in the first cup. The third cup contains the same fraction alpha of the second cup, and so on. What is the maximum value of alpha so the person drinks no more than 3 times the amount of tea in the first cup, however many drinks they take? Okay, so we have, in the first cup, we're going to say we have 1 lot of tea. In the second, we have a fraction of that, and the fraction is alpha. So we multiply it by alpha, so that's the second term. the next one is alpha squared, because you multiply by alpha, and it's alpha cubed. So what we're asking is what value of alpha for 1 plus alpha squared plus alpha cubed, ... Does this equal 3, basically? What's the maximum value of alpha? So we can see that this is a geometric series, with the first term being 1, and the ratio between each term being alpha. So the sum to infinity, as this is, because it goes on and on, this equals a over 1 minus r, that's a formula. So it equals 1 over 1 minus alpha, and we want this to equal 3. So if I just bring this up here, we have 1 equals 3 minus 3 alpha, and then we have, minus 3 alpha equals minus 2, so alpha equals 2/3. So this is the maximum amount. So that is C. Okay, so number 6, a stationary wave is set up on a string of length L. If the centre and the ends of the string are held fixed with 0 displacement, what wavelengths, lambda m, can this stationary wave have? In the table below, m denotes any positive non-zero integer. Okay, so it's held between two bits. No, it's the centre and the ends. Okay, so we have the centre, the ends, and centre. Okay, what wavelengths of lambda m can this stationary wave have? Well, the smallest wavelength, or the one with the largest wavelength actually, would be something like this. Okay, these squiggles aren't meant to be there. So the string is of length, if this is length L, then in this case we know L equals lambda. Okay, so the next kind of stationary wave formed is actually going to be this one here, because it's going to be oscillating as if these points are fixed in place as well, because it'll be stationary. You can't have one which is that would be like this here, that's just not how they form like this. Okay, so we have this one where L equals 2 lambda, and then the next one similarly will be L equals 4 lambda. So we're asking it in terms of lambda m. Well, we know that here, in this one, lambda equals L over 2, and in this one here, lambda equals L over 4, and the first one we have lambda equals L. So it's always L over 2 m, because when m equals 1, we have this one, it's always a multiple of 2, basically. So that's C. So 7, a car of mass m is travelling along a straight and narrow road at a speed u. A cat walks into the road a distance d in front of the car and stops in the middle of the road. What constant force must be applied to the car so that it does not hit the cat? The road is too narrow for the car to try and pass the cat without hitting it. So we know that the work done by the force needs to be equal to the kinetic energy. The work done in stopping the car. So work done equals force times distance. We know that. And this equals half m, and the speed is u squared. So then rearranging this in terms of f, we have f equals mu squared over 2d. Okay, so where is it? F equals mu squared over 2d, and this is this one. And the force is negative, because in the direction of motion d is this length, going like this way, we know the force will be negative, so it's A. So 8, what is the value for x for which y has a minimum in the function y equals x minus 3, x plus 1? Okay, so y equals, expanding this out with x squared, minus 2x minus 3. So we know that dy by dx equals 2x minus 2. So we know from this, when this equals 0, we know x equals 1. Now, so that's like the minimum because it's a positive quadratic, so it will look like this, and x equals 1 here. That's 1. Alright, so 9. What's the equation of the line which intersects y equals 2x minus 2 at right angles and at position x equals 1? Okay, so if we look at y equals 2x minus 2, the equation of the line which intersects it at right angles will be the perpendicular line. So we know that if m1 equals 2, m2 will be the negative reciprocal of this, so minus half. We know that x equals 1, y equals 0. So we're looking at a line of these properties. So we have y minus 0 equals m outside of x minus x1, which is 1. So here we have y equals minus a half x plus a half, multiplying that out, so that's b. For which range of x is the inequality x cubed minus x squared minus x plus 1 bigger than or equal to 0 satisfied? So we're going to try and find a common factor of it, and then we're going to factorize it, find the intersection points, and we're going to look at what the curve looks like. So looking at this curve here, let's try and sub some values. Well, actually, in the answers here, we can see that it has 1, 1, 1, minus 1, minus 1, 1, minus 1. So it would be worth trying 1 or minus 1. So just thinking about putting 1 into it, we'll have 1, minus 1, minus 1, plus 1. So that will be 0. So f of 1 equals 0. So that concludes that x minus 1 is a factor. So if x minus 1 is a factor, I'm going to divide 3 by x minus 1. So we need an x cubed here. So this is x squared, this is minus x squared, that's fine. Then we need minus x here. So we know that this is minus 1, and then this is 1, and that's all we have. So then we know the curve is, we know it's x minus 1 times x plus 1 times x minus 1. So these are repeated roots, so I'm going to write this as squared here. So if we draw the curve, we know that it intersects at 1 and at minus 1. And if we look at this equation here, we know it goes through here as well. But there's a repeated root at 1, which means it will just touch it. So like this. And it's a positive cubic, so that's what it will look like. So when this is greater than or equal to 0, well, we can see here that for this region, it's all greater than or equal to 0. At point 1, it is 0. So this is when x is bigger than or equal than minus 1, which is E. Okay. Question 11. A rectangular building with sides 50 metres and 100 metres long has a flat roof on top of it. The roof has a mass per unit area of 100 kilograms per metre squared. The walls are 10 centimetres thick and can take a maximum stress of S max, which depends on the material of the wall. The values of S max of 5 building materials are, and then, so here are the values. Which materials could be used so that the walls will support the building, assuming that the mass of the walls is negligible? Okay, so first we want to find the area of the roof. So it looks something like this. Sorry for the bad sketch, I'm on a tablet. So we know this is 10, this is 100, this is 50. So the area of the roof will be 100 by 50, which equals 5,000 meters squared. And then we know that the mass per unit area is 100. So we know that the mass of the roof will just be this times 100, which is 5,000,000, so 500,000 kilograms. And then we know that we need to find the force of the roof, which is the weight, which will just be this times 10, which will be 5 million. newtons. And we know that stress equals force over area. So we need to find this area here. So this will be 10 centimeters, which is 0.1 meters. I'll write that out. So we know it's 0.1 times by 50 times by 2. Added on to this is 100 here, but we're taking away these 0.1 sections. So this will be 98.2 times by 0.1 times by 2. So if we factorise this out, we have 0.1 times 2 times 50 plus 98.2. So we can actually approximate this 98.2 to 99.2 even, because it's basically the same number. So we have 0.1 times 2 times 150, which is 330 meters squared. And this is newtons per millimeter squared. So this is, the conversion factor is between a meter and a millimeter is 1,000, but when it's meters squared, it's 1,000 squared. So we know this is 30 times 10 to the 6 millimeters squared, which is 3 divided out by 10 times this by 10 times 10 to the 7 millimeters squared. So we know that the stress it can take, or the stress it is taking, is 5 times 10 to the 6 over 3 times 10 to the 7. Actually, if this was 30 and this was 6, that'd be easy to work out, because we know that 5 over 30 is 1 over 6, simply. And 1 over 6 is, half of a third, so 0.333. Half of that is 0.1666, I think, but just around 0.17. So that's the stress that the walls can take. So if we look up to this, we can see that these are all much bigger than it. So any of the materials above can support the building. Okay, so question 12. A light ray passes through an infinite stack of thin transparent plates. The refractive index of these plates increases slightly by a constant factor from one plate to the next. The ray enters the first plate, making an angle of theta 0 with the surface normal. The ray's angle to the normal changes at each new interface. At the ith interface between the plates, the ray makes an angle theta I to the normal. Find the limiting theta infinite for the angle theta I when the ray has traversed an infinite number of plates. Okay, well, we have a plate here, plate here, plate here, plate here, and we know that the refractive index increases in each one, so that means it will be bent more towards the normal at each thing, but it will never get there, never get direct at the normal until the infinite one. So we need to find a limiting value for the theta I when it makes the angle. Well, because it's bending more and more towards the normal, the theta infinite is going to be 0 degrees because this angle is getting smaller and smaller and smaller. So, question 13. Consider the network of capacitors shown. All capacitors in the network have the same capacitance C. Assume the capacitance combines as follows. Two capacitors in series combine the capacitance in the same way that two resistors in parallel, and vice versa. Find the total capacitance, C tot. Okay, so this is just like a reverse resistance. So for this area here, we have C. So that's 1 over C plus 1 over C to the minus 1. Or if you know how they add, we know that this is simply just C over 2, because that's how resistors, that's how it works out when you have two next to each other. So this loop here, we have 2C, because it's just the opposite. So 2C there, and then this is just a C. And here we have 3C in this area, because it's like 3 in parallel. So redrawing this, we have C over 2. Sorry, just 3C, C, 2C. Okay, so 1 over C plus 1 over 2C. 10 minus 1 equals 2C plus C over 2C squared to the power minus 1. So this is 3C, we cancel out that. So this is 2C over 3 for this one. So now we have C over 2 plus 2C over 3 plus 3. 3C, sorry. So to get this, we just need to kind of add the fractions accordingly. So we then have 3C plus 4C, 3C plus 4C over 6 plus 3C over 1. And then we have 7C plus 18C over 6. 7 plus 18 is 25C over 6. So this is the answer. Alright, so 14. Solve the following equation for x. Log x of 25 equals log 5 of x. So log x of 25 equals log 5 of x. So this is 5 squared, I can see here. And then this is 2 log x of 5 equals log 5 of x. Interesting. So what I'm going to say is I'm going to say y equals log x of 5. So here we have x to the y equals 5. And for this one here, I'm going to say z equals log 5 of x. So we get 5 to the power of z equals x. So I can then put these two together to find out the relationship between this and this. So I get 5 to the zy equals 5. So we know that z times y equals 1. So z times y equals 1. So we know that that's the log x5 times log 5x equals 1. So actually, just inversing that, we get log x5 equals 1 over log 5x. Okay, so this is the equation that we just derived. You may have known this before, but it's very easy to work out in the exam. So I'm going to say that this here is 1 over log x5. So multiplying through by that, we have 2 times the log x of 5 squared equals 1. So, actually probably be easier to do it the other way, but never mind. So we have log x of 5 equals 1 over root 2. So we get x to the 1 over root 2 equals 5. So now raising both sides to the root 2, we get x equals 5 to the power of root 2. Okay, but here it's actually plus or minus 1 over root 2 because there has to be two solutions because obviously we're squaring something. So then this is x to plus or minus root 2. So 15. A car is initially stationary. At times t0, it starts to move at speed v1 for time delta t1. Immediately after this, it moves at a speed v2 greater than v1 for time delta t2 less than delta t1. After this time, it's stationary again. Using this information, sketch a graph of speed v versus time t. Label all axes sufficiently so that the graph is quantitatively accurate. Okay, so if we just draw a simple vt graph here, Well, we're told that we have two speeds, v1, v2. It starts at time 0, which we're going to call here. We know it has t0 plus delta t1. And then it has 4 times delta t1. And then delta t2 is less than delta t1, so this portion is going to be closer. Can do it like that. Oh, come on, I'll make this smaller. Oh, goodness sake. Okay, just keep that. And then this one here is t0 plus delta t0. Okay, so we know that it's faster in the second block than the first block. So I know that this is v1 and this is v2. Okay, and that's all there is to it. So, B, from your graph, I'll just mark this as A. And this needs to be t in seconds and v in meters per second. So determine the average speed v of t of the car while it is moving. Okay, well, we know that the average speed is going to be like the total distance over the total time. So the total distance is v1 delta t1 plus v2 delta t2, just like the area under these curves, over the total time, which is just delta t1 plus delta t2. So they want us to compute it when v1 equals 1 and all of these ones are combined. So when we plug in these values, we have 1 times 2 plus 2 times 1 over 2 plus 1, which equals 4 over 3, which equals about 1.33 meters a second. Okay, so now part C. We have now draw the graph of V versus distance S using the numerical values for speeds and times given in section B, and label the axes as before. Okay, so we know that we're going to start off at 0 distance, and we have 2 meters here, and then we have another 2 meters here, which is 4. And we know for V1 it was 1, and for V2 it was 2. Okay, so now let's just draw these boxes. Okay, there we go. So now part D. From the second graph, find the average speed, Vs, known as the distance weighted average. So, this is a bit weird, but I guess it's just the same, but instead of using delta T1, we use delta S1. So we now have V of S, which equals V1 delta S1 plus V2, wait, let me just move this. Plus V2 delta S2 over delta S1 plus delta S2. And they want us to provide the numerical value using the values before. So if we look at the V1 delta S1 here, we know that it is V1 here, delta S1, so we know it's 1 times 2 plus V2 delta S2, V2 is 2, delta S2 is 2, plus 2 times 2, over the distances, which is 2 plus 2. So equals 2 plus 4, which is 6 over 4, which equals 1.5. meters per second. So now, part E, we have which of the two averages is equivalent to the conventional definition of average speed. Well, that is clearly the time weighted average because it's total distance over total time. So we know that V of C equals V of T. So last part F, study the mathematical operation that should be applied to the curve of V of T to compute V of C if we assume V to be any function of time or distance. So we need to find the total area under the curve of V of T to find the total to find the distance, and then we need to divide that by the time. So this will look like the integral between t naught, I guess. T naught and T naught. Look, let me just do it like this. Okay, between T1 and T2 of V with respect to T over T2 minus T1. And is that the question? No, it says state. Okay, so you integrate with respect to time, to time, like that, and divide by total time. Okay, there you go, that's part F. So, part 16. Consider the cross-section of a pencil where a concentric circle of radius r sits at the centre of a regular hexagon. If the black area is a quarter of the total area and a hexagon, what is the length of the dimension x in terms of r? Okay, so I'm just going to zoom in on this hexagon. So what we need to do is we need to find kind of the area in white, and we need to find the bloody area of the hexagon. Then we need to find the black area, and then we just need to turn that into an equation, and then just find x in terms of r. So let me just do it. Wait, what was the... Sorry, I'm just reading the question. What is the length of dimension x? Oh, here's x. Okay, so x is like this distance here. I'm gonna get a smaller pencil as well, sorry. Okay. So, if I have x here, I can divide the hexagon into rectangles, actually. So, I can make it look like this. So how many angles do we have here? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 360 divided by 12 equals 30. So we know that each one of these is 30. We have a distance here, x. And we also have this distance here, I'm going to call y. So we know that the tangent of 30 equals y over x, and the tangent of 30 is 1 over root 3, if you don't know. You can work it out by drawing this triangle here, where this is 30, this is 60, this is 90, and then we have root 3, 1, 2, so tan of 30 is opposite over adjacent, which is 1 over root 3. Okay, so what we need to do now is we need to find the area of the hexagon. So the area of the hexagon is we have 12 of these rectangles. So we have 12 of these rectangles here, which is times a half xy, which equals 6xy, which equals, we have hit from this equation here, we can see y equals x over root 3. This equals 6x squared over root 3. So we then know that the black area, or the area of the circle, equals pi r squared. So we know that 6x squared over root 3 equals 4 pi r squared, because the area of the hexagon is 4 times the area of the circle. So from this, we can simply just, excuse me, we can find x in terms of r. So we know that x squared equals 4 over 6, which is 2 over 3 root 3 pi r squared. And x equals square root 2 root 3 over 3 r. So that's that. So question 17. To which order should you expand 1 plus x to 9 in the integral 0 to 0.1, 1 plus x to 9 dx, so that the approximate integral agrees with the exact result to better than 10%? Okay, excuse me. So we need to find the integral. So integrating between 0 and 0.1 of 1 plus x to the 9 dx. This equals, actually I'm going to check, do we need to, yes. Okay, yeah, we can use the calculator on this exam, by the way. Sorry, I should have mentioned that at the beginning. Actually, I actually forgot a little bit. Okay, so this integral here is the integral between 1 plus x to the power of 10 and a tenth of this. Because look, if we differentiate this, you multiply by the power, take 1 by the power, then multiply by the derivative on the inside, which is 0. So 0 to 0.1. So working this out, we have 1 plus 0.1, which is 1.1 to the power of 10, minus 1 to the power of 10 over 10. Okay, so this is 1.1 to the power of 10 minus 1 over 10, which equals 0.159374246. That's as much as my calculator does it. So finding plus or minus 10% of this, we need to multiply this by 1.1 to find an upper limit, and to multiply it by 0.9 to find a lower limit. So the upper limit is 0.17531166706, and then the lower limit is multiplied by 0.99 to find a lower 10%, which is 0.14343688214. So then what we're going to do is we're going to use the binomial expansion to expand this out, see what number we need to get the result. So we have the integral between 0 and 0.1 of this expanded here is 1 plus 9x plus 9 times 8x squared over 2 plus 9 times 8 times 7 x cubed over 6 plus dot dot dot, I'm going to say, because I ran out of space. We don't need that many terms anyway. So integrating all of these terms, we have x plus 9x squared over 2 plus 12x cubed plus 21x to the 4th. Dot 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 between 0 and 0.1. So now calculating all of these terms here, we have when you put in 0, this will just cancel out all of these terms. So we're only looking at putting in 0.1. So we have 0.1 plus 9 times 0.1 squared over 2, which is 0.045 plus 0.1 is this, which is 12 times 0.1 cubed, which is 0.012. But actually, wait, yeah. We can see that this is 0.134 here. But if we just use 2 of these terms, we have 0.145, which is actually inside the limits, just with 2 of these terms. So we only need to expand up to the second order to the x term. There you go. So that's it. Okay, so question 18. The diagram shows 2 spheres of mass m suspended from wires of negligible mass. The length between the pivot points and the centres of each sphere is L. There's 2 suspension points lie on a horizontal line and are separated by a distance x. This system is in equilibrium. Take the total acceleration due to gravity to be g. You may assume that delta x is much, much smaller than L and delta x is much, much smaller than x. Show that the small deflection delta x by which the gravitational force Fg between the spheres will deflect them from the vertical is given by delta x roughly equal to, and then this equation, where g is Newton's gravitational constant. Clearly state all assumptions you make and show all your workings. So, let me just zoom out a little bit more. So, part A. So this is quite a big question, but the first thing I'm going to do is I'm going to label my diagram a bit more. I'm going to call this a T here. And we have a gravitational force here, and we have a weight here of mg. So we can turn these into kind of equations of motion, where we know that T cosine theta, like this force, the vertical force here, equals mg. Okay, and then we also know that this is resolving up. And then we have, resolving that way, we have T sine theta equals the gravitational force here. And the gravitational force is F equals G, mm, so m squared, over the distance between them, which is x minus 2 delta x squared. So I'm going to say T sine theta equals this. G m squared over x minus 2 delta x squared. So this is just Newton's gravitational force formula. So we also know that from this kind of triangle here, we know that L sine theta equals delta x. So we know that delta x over L equals sine theta. But because this is a small angle approximation, we know that this roughly equals theta, okay? But another small angle approximation is we know that tan theta also roughly equals theta. So this roughly equals tan theta as well. So you'll see why this will come in useful later. So if we just have equation 1 here and equation 2 here, what we can do is we can do 1 over 2, or in fact 2 over 1, which equals g m squared over x minus 2 delta x squared, multiplied by 1 over mg. We know that this equals t sine theta over t cos theta, which is just equals tan theta, okay? Which roughly equals delta x over L. So we then have gm squared over x minus 2 delta x squared times 1 over mg equals delta x over L, okay? So expanding this thing down here, we have gm squared over x squared minus 4 4x, excuse me, minus 4x minus 4x delta x plus 4 delta x squared times 1 over mg. Okay. So, yeah, that's that. Now what we've got to do is multiply through by the g. So we know that delta x over L roughly equals, and then this cancels with this here. So we have gm over gx squared minus 4gx delta x plus 4g delta x squared. Now, if we look at this here, delta x squared, we can assume that this is 0. And the reason why is because we know delta x is absolutely tiny. It's like very, very small number. So we're just going to like not ignore this term. And also, if you see here, if we then multiply through by delta x, multiply through by this, we'll get a quadratic in delta x squared, which is what we want. So let me just trim this up. All right. So then multiplying through, we get L m g, big G, equals g x squared delta x minus 4xg delta x squared. And the reason we're not putting this delta x to 0 is because we can clearly see up here that this is like comes from a quadratic, so we're going to keep this until we solve it. But it's just if it's cubic, then it makes it a lot more complicated. So then if we move all these to one side, we can see that A equals 4xg, B equals minus gx squared, and C equals lmg. So then solving for delta x here, if I've just added this and minus that to the other side. So then we know that delta x equals minus b plus or minus the square root of b squared minus 4ac, which is 16xg lmg, all over 2a, which is 8xg. So we can split this off into these two terms here because this term can split off. So we know that the g cancels, one of the x's cancel, so we just get x over 8, which is a good sign. That's what was in our original formula. Plus the square root of g squared x to 4 minus 16x glmg all over, and I'm going to move this inside the bracket so I can make more cancellations, so I get 64x squared g squared. So then this equals x over 8 plus or minus the square root. So in this we can see g squared cancels with, in this term here, sorry, g squared cancels with g squared, x to the 4th x squared. So then we're just left with x squared over 64 minus, in this one here, we can see the 16 and 64 cancel, x squared, g squared. So we're just left with lmg over 4gx. And what do we have here? Oh, okay, so there we go, we basically have it. So we have x over 8 plus or minus the square root of x over 8 squared minus lmg over 4gx. So then what we have to do is we have to like look at this and see why they've chosen the negative solution. And the reason why is if we look at delta x here, we know that as the mass goes to 0, okay, we know that this term here, we know that delta x will have to go to 0, okay? And the reason why is because if the mass is completely 0, then it will just be like hanging down, so delta x will be 0. So what satisfies that? Well, if m equals 0 here, we have delta x equals x over 8 plus or minus x over 8. So the only way for this to be 0 is if we choose the negative solution. So that's why it's a negative. Okay, so we say, therefore, delta x equals this with the negative. Okay, so part B. This says, spheres are now both electrically charged with the same positive charge Q. How big must Q be so that the wires will hang vertically again? Hence, the force between the two spheres electrically charged is given by Fq equals K, Q1, Q2 over R squared. Okay, so this is just like what they said here. So we know that this is counteracting the gravitational force, because the gravitational force is going that way. We know the electrical force will be going this way because they have the same charge. So we just know this has to be equal to Gm squared over R squared, and this is not Q1, Q2, this is QQ, so Q squared. So multiply through by R squared, this, these cancel out, and then we just get Q equals square root of Gm squared over K, which equals M root G over K. Okay, so question 19. So consider the above circuit. The filament lamp A consumes an electrical power of 100 watts. When this is alone connected to the voltage of U equals 100, okay? Okay, 100 watts. Filament lamp B consumes 20 watts when it alone is connected to the voltage, okay? So when the switch is closed, which lamp will be brighter and why? Okay. So the first thing we're going to do is we're going to figure out the resistance of the lamps, because when they're alone in the circuit. So we know that P equals V squared over R. So R equals V squared over P. So for lamp A, we have R equals 100 squared over 100, which equals 100 ohms. And then for lamp B, we have R equals 100 squared over 20, which equals 100 times 100 over 20, which equals half a thousand, which is 500 ohms. Okay, so next, what we can do now is we can work out the power of each of these bulbs when they're connected in this circuit, and whichever has the higher power will have the higher brightness. And yeah, it actually says that here. So for A, we know that P equals I squared R, and we know that the current is equal in this series circuit. So then we have the power of A over the power of B is going to equal the resistance times, the current times like the value of the resistance. So the R for A is 100, so we have 100 squared I squared over 500 I squared, not 100 squared, so this just equals, so this just simply equals 1 over 5, so we can see that PB is higher. So part B, we have how the answer changed if the lamps were wide and parallel rather than series. Well, in parallel, look something like this. We know that the voltage will be the same. So if this is 100 volts, we know that going through here would be 100 volts. Going through here would be 100 volts. So we know that the resistance of A was 100, I think. Yeah, 100 ohms, and the resistance of B is 500 ohms. So we can now work out the power of both. So we know that P equals V squared over R. So now what we can do is we can say that the V's are going to be the same. So if we do PA over PB, this equals V squared over 100 over V squared over 500, which equals just 500 over 100, which is just 5. So P of, which is 5 over 1, as you can see here. So we know that A is brighter. Okay, so question 20. In a crystalline material, planes of symmetry are labelled using triplets for integer numbers of the form HKL. E.g. 100 is equivalent to 100. Okay, so not numbers, just some stuff. It doesn't matter what they mean. It is possible to determine these for multiple planes of symmetry. From the knowledge of several such triplets, the microscopic structure of the material can be inferred using the following rules. If for all planes of all positive integer values of HKL are possible, then there's a simple cube lattice. Okay. If for all planes, all positive integers, okay, so if we have HKL bigger than 0, it is then a simple cubic lattice. If we have H plus K plus L equals 2n, where n is positive, then this is a body-centered cubic. And if H, K, L either all even or all odd, it has a face-centered cubic lattice. Okay. And it says, note 0 is an even number. So during the analysis of the data from such an experiment, the following 4 planes of symmetry were found. 111, 200, 220, and 311. Okay. What type of lattice did the material in these experiments have? So I'm going to write 111, 200, 311, and 220. Okay, this is part A. So basically what I'm going to do is I'm just going to work out which one of these have which. So 111, this is all bigger than 0, so this is a simple cubic lattice. So it has A. Do they all add up to an even number? No, they don't add up to 3. So it's not a body-centered cubic. All even or all odd, it is. So then it's a face-centered cubic, C. So now for 200, they're not all bigger than 0, so it's not A. They all add up to an even number, so it has B. And they are all even, so it is C. So now 311, they don't all add up to an even number. They're all bigger than 0, so it has A. They're all odd, so it's C. Then 220, we have not all bigger than 0, so not A. They all add up to an even number, so it has B, and they are all even, so it is C. So now, looking at all of these, you can see they all have in common C. So that means that it is C, which is a face-centered cubic. All right. So part B, in a material with some form of cubic lattice, the distance between the planes of symmetry is given by D equals A over the length, where A is the constant length, that is usually the order of refraction of a nanometer. Determine the best estimate for A. Okay, so we want this. Can I move this? Okay, So now, what we have to do is we're going to have to like work out our values for A, for all of these things, and then we're just going to average them, and I'll give us our answer. So we know that A equals D square root h squared plus k squared plus l squared. All right, so plane 111, okay, D in nanometers. So let's just get a calculator and try to work that out. So our value for the first one is going to be 0.224 times the square root of 1 squared plus 1 squared plus 1 squared, which is actually just 3. Okay, and this on the calculator is 0.3880. Okay, so A2, we have 0.195 times the square root of 4. So just like basically doubling that, we get 0.39. So A3 we get 0.137 times the square root of 2 squared plus 2 squared, which is 8. And this equals 0.3875. I'm just going to get to 4 decimal places, because I think in the question, did it ask? No, but these are all to 3 decimal places, so we're just going to give it to the amount that is said. So 4 decimal places will be plenty. So A4, this equals 0.117 times the square root of 3 squared plus 1 squared plus 1 squared, which is 11. 0.117 times root 11. Okay, sorry, just checking if the microphone's on. This equals 0.3880. So now, averaging all of these up, we get A equals plus we get 0.389 to 3 decimal places. So that's B. So now part C. A cube of the material has length L in each dimension where L equals NA, and N is a very large number. Pressure is applied to opposite sides of the cube. The volume of the cube remains constant, but one of the cube's dimensions reduces to a length of L prime equals 2/3 NA. What is the new length of the deformed object in the other 2 dimensions? Okay, so wait, what is the new length of deformed objects in the other 2 dimensions? Excuse me. So first, we have a cube with like L sides. So this is L, L, L. So we know that the volume equals L cubed, which equals actually N cubed, A cubed. And then after the deformation, we know that it's just applied to 2 sides, I believe, to 2 opposite sides of the cube. So the volume remains constant, but one of the is reduced. Okay, so then after, the volume is constant, so we know that all of the sides have to change. If the pressure has been applied like on this side, we're going to say this equals 2/3 NA. And then this, we're going to say this is the new length x. So we know V equals x squared 2/3 NA. So we know that these volumes are equal. So just setting them equal, then we can work out what x is. So we have x squared. Firstly, we can divide through by this and this. So x squared equals 3 halves n squared a squared. So we then know that x equals root 3 over 2 NA, which is actually L from before, L equals NA. So this equals X equals 3/2 L. And that's the question. So, part 21. A child of mass m stands on a platform which rotates freely at an angular speed omega. The child's centre of mass is initially at a radius r0 from the axis of the platform, as shown in the figure below. The child now slowly pulls itself closer to the centre of the platform. So the minimal force Fr needed to pull the child closer to the centre as a function of the radius. So we know that the force, acting in the direction, is m omega squared r. You should know that from just your, your thing. You should just know that. So the minimal force F of r needed to pull the child closer to the centre as a function of the radius r. Okay, so we know that omega is also going to be changing at this time, because as the child pulls closer, it's going to actually increase. Is it going to increase? Yeah, it's going to increase the omega. So omega is actually a function of r. So then omega of r squared. Okay, so that's part A. Part B. Find the mathematical expression for the work done by the child when this has reached the centre of the platform. And we have a hint here. The work done along the path to be work equals the integral of f of s ds, where f is the force. Okay, so it should be easy enough. So when this has reached the centre, so we know it's done a distance of r0, starts at 0, ends at r0. So we get this equals the integral of just this thing. Oh no, sorry, this thing here. So we have between 0 and r0 of m r omega of r squared dr. Okay, so that's part B. Part C. Into which form of energy is the child's work converted, and what will qualitatively happen to the angular speed omega as the child approaches the centre? So I kind of just said this before, but the energy will be put into rotational, kinetic energy. So basically, it will be kinetic energy, but it's kind of rotational because we know the rotation will increase. So if you imagine an ice skater, if you've done this, then maybe you know. If you stand like this, you'll be going around at a speed. If you then go into a ball or into just very thin, then you'll be going a lot faster. This is also on some of those things in play parks with the handles on, and then you can stand like this. And if you're on the outside, you go a bit slower, but if you're really, really tucked in, then you'll go a lot faster. So we know that omega will increase. So part D, the angular momentum J of a system of a child and platform is a conserved quantity during the above process. It is defined to be J equals I omega, where I is the moment of inertia of the system, which is given by I equals mr squared plus IP. I equals mr squared plus IP. And J equals omega I. Is that it? Yeah. No. Yeah. Okay. Where IP is the constant moment of inertia of the platform. Find an expression for the angular speed omega r as a function of the radius of the child's centre of mass. So we know that J equals I omega, so simply just plugging this in, we'll get J equals omega mr squared plus IP, which is a constant. So what we can do is omega equals J over mr squared plus IP. Because, did it say J is conserved quantity? Yeah, so these are just numbers. This is a number, this is a number, this is a number, and then we just have it in terms of r squared. So that's our omega r there. So part E now, we have find the total work done by the child when he's reached r0. r equals 0. Hint, the integral of x, this thing here, I'm going to borrow this down here. So it's actually going to do the integration for us as well, which is quite nice. Sorry, let me just make this a bit bigger. Okay. So the integral was the work done. It equals the integral from 0 to r naught of mr omega r squared dr. So what we can now do is we can put in our here, we can put this into here. So we get this equals the integral from 0 to r naught of m r, and then it's just that squared, so j squared over m r squared plus ip squared dr. And okay, so what I'm going to do is I'm just going to move this all up. Okay, so now what we can do is we can factor out the constant terms. So we can take out an m, a j squared, and actually to get it into this form we want here, we know we need the r squared to be by itself, so we need to divide out by m in this, which will be the integral from 0 to r naught of I'll just take out now, m j squared, r over, and then I'm going to divide through by the m, r squared plus ip over m. So when you bring that out of the bracket, it's going to be over m squared. So we can just cancel that. So, yeah, dr. So you know that this equals j squared over m. But we now have this here, which is now in the form that we want, I believe, because we have r squared and our a equals ip over m. So I'll just write that out to make it simpler. So we know that x equals r and a equals ip over m. So we know that now the integral of this, we can simply just do it, is minus 1 over 2 outside of a plus x squared, which is ip over m plus x squared, between 0 and r naught. With respect to r, so we're going to be subbing in the r naughts. So this equals minus j squared over m outside of, because just taking this minus out there. Then into substituting, so we have minus 1 over 2 ip over m plus r naught squared. Oh, that's not minus. Minus 1 over 2. If r squared is 0, then we just have 2 ip over m. So now, just cleaning this up a little bit, we can just, what can we do here? ip over m is here. So we know that this m just goes to the top, which cancels out with these two. And then, so we just have minus j squared outside of 1 over 2 ip plus r naught squared m minus 1 over 2 ip. So we can factor out 2 here, and then just reverse the negative sign to get 1 over ip. Let me just make the last one look readable. So 1 over ip minus 1 over ip plus m r naught squared. That's the final answer. So part 22. Determine the area inside a circle defined by this equation, but outside the triangle bounded by the 3 lines below. the area inside the circle, but outside the triangle. So we need to work out the area of the triangle, defined by these lines, then work out the area of the circle, and just the area of the circle minus the area of the triangle. So first I'm going to put this equation in the form where we can find r squared, so we can find the area of the circle. So we have x minus 4 squared minus 16 plus y plus 2 squared minus 4 plus 4 equals 0. So we have x minus 4 squared plus y plus 2 squared equals 4 squared. So we know that r equals 4. So we know that the area of the circle is pi r squared, which equals 16 pi. So now to work out the area of the triangle, we know that we're going to have to find the points where all of these lines intersect. So simply just trying to draw it a little bit with x minus 7. So I'm going to draw like that. A fifth, 29 over 5. What is that? That's around 6, I think. Yeah. So that's going to be minus here plus 2/5. So it's going to look like that. And then x equals 7. So it keeps going along here. And then when x equals 7, we know it's there. Okay, so that tiny little triangle there is the one I'm trying to find, which is a bit annoying that I drew it like that, but whatever. So x minus 7, a fifth, 2x minus 29, and x equals 7. So we know that the intersection, I'm going to call this point A, this point B, this point C. So you know that point A is the intersection between x equals 7 and x minus 7. So we have x equals 7, and then y simply just equals 0, because putting 7 into that. So then part B, with the intersection between these two, a fifth of 2x minus 9 equals x equals 7. So we have a fifth of 14 minus 29. So 14 minus 29 equals minus 15, divided by 5. This equals minus 3, so that's y. So we have 7 minus 3. And then part C is the intersection of these two lines. So we have a fifth of 2x minus 29 equals x minus 7. So we have 2x minus 29 equals 5x minus 35. So then we have 3x equals 35 minus 29, which is 6. So we get x equals 2. And y equals x minus 7, which is minus 5. So this is just 2 minus 5. So now, to find the area of the triangle, I'm going to draw it out a bit. So this is A, B, C. So this is 2 minus 5, B is 7 minus 3, and A is 7, 0. So actually, we can actually figure out the base here, because we can do this. This side here is 3, and then the horizontal side here is just between 2 and 7, which is 5. So now we have the base and height, so we can just do half base times height equals 15 over 2. So then we know that the area is just 16 pi minus 15 over 2. So that's that. So, question 23. Given that f of x equals x squared minus 2 over the log of 3x plus 10, determine the range of x for which f of x is real and finite. And this is the last question. So, we know that 3x plus 10 firstly has to be bigger than 0, because whatever inside the log has to be bigger than 0. So this is just when x is bigger than minus 10 over 3. So that's the first point. The second point, we know that x squared minus 2 has to be bigger than 0, bigger than or equal to 0 actually. So this is when x, if we draw the parabola here of x squared minus 2, we have root 2 minus root 2 there. And for this to be bigger than or equal to 0, we need x bigger than or equal to root 2, or x is less than or equal to minus root 2. So we know that also that the log of 3x plus 10, this cannot equal 0. And this happens when, for the log of something to equal 0, if we just raise them both, if we just both of them, basically, we get 3x plus 10 equals 1. So we get x equals minus 3. Yeah. Okay, so that's where it cannot equal minus 3, by the way. Okay, so now what I'm going to do is draw a line and where all of these stuff intersects. We know x needs to be bigger than minus 10 thirds. Yeah, I'm going to write it on the bottom. Okay, minus 10 thirds. And then that 10 over 3 is bigger than minus 3. Yeah, so then we have minus 3 here, and we have minus root 2, and we have root 2. And is that all the things we need? Yep. So we need that x has to be within these bounds, and it needs to be bigger than minus 10 thirds, so within these bounds, and then it also cannot equal minus 3. That's it. So the area where all of these intersect is we have minus 10 over 3 less than x less than minus 3, and then we have